I'm glad my flight didn't get delayed. I arrived at 1 p.m. here, so I'm able to speak. Okay, so I'm going to tell you some new developments in the physics of rhombohedral multilayer graphene. And these are the people who contribute to the work. Again, I have to point out these two gentlemen here. My postdoc, Zhengguang Lu, is super capable, do everything that you wish a postdoc can do. And graduate student Tong Han is by the end of his 4th year. But he has done so much that I think he can graduate at any point if he wants, but I'm going to keep him for another 2 years. Okay, and we have a collaboration with our colleague Rhea Shree and his student Sam, and we got theory support from Liangfu, Fan, and we got nice HBM crystal from Japan. Okay, so a brief reminder for you what we have seen in pentalayer rhombohedral graphene HBM Moiré system. When we push the electrons to the layer that's away from the Moiré, we observe integer and fractional quantum anomalous Hall effects. Okay, and at that time we have 6 fractions, and you already noticed that 5 of them looks sort of like similar. That the RxY changes monotonically. Of course, the 2/5 is slightly different because it's on the boundary, but most of these fractions are like kind of going down monotonically and slow down at a plateau before it goes down further. Well, 2/3 is slightly different, okay? 2/3 is a local maximum in RxY, and so it feels like there's some competing states nearby. And similar observation was made in Xiaodong's fraction fitting 2/3, okay? It's also a local maximum, and there's some competing state where we're all guessing what they are. And I'm going to show you, at least in our system, what that competing state is. And just to, make sure that, I don't think I usually show the strata formula thing, but it works perfectly for the 6 fraction states. Okay, so everything makes sense. So I'm going to show you 3 things today. Some more experiment on fractional quantum anomalous Hall effect, and FCI in 4 and 5 layer rhombohedral graphene, HBM Moiré. And then I'm going to show you what I call as extended integer quantum anomalous Hall state. And then I'll show you some superconducting states, okay? Looks like different topics, but they are actually connected. So the first thing I want to show you is that, in addition to in-plane DC transport measurement, our colleague Ray is an expert measuring capacitance, and that tells you the electronic compressibility. So we made a sample for him where, it's a different sample from the transport device, right? So this one, you have good electrical contact when the electrons are pushed towards the Moiré. So your electrons feel strong Moiré potential. And you can measure compressibility, and you get a map like this. Bright feature here means incompressible or gapped. And you find that, okay, this side here corresponds to when you polarize the electron to the Moiré, and this side corresponds to when you push the electron to be away from the Moiré. You can see there's contact issue because there are a lot of random features here. And on the Moiré proximal side, what you can see is, there's insulating state at fitting factor 1, 2, and 4. And there's something here at 1/3 and 2/3. And it turns out those 2 states are the CDW state, or generalized Huygens crystals, when it's commensurate with Moiré. When you apply magnetic field, okay, and you do line cut at position 1 and position 2, you actually can induce a state that has a fractional slope, this green lines indicating here. So it could be like, at a 0 magnetic field, CDW is the true ground state, most stable. But when you apply a magnetic field, you actually can observe a transition from CDW to FCI, and you get this is a fractional Chern insulator state with slope of -1/3. There's also a state with slope -2/3 stemming out from fitting factor 2/3. But there's also a Chern insulator state, integer 1, with slope -1 stemming from fitting factor 1. Depending on how you cut it, if you cut it properly, you will get something like this, that this FCI persists almost to 0 magnetic field. Okay? Not 0 magnetic field, but something like 0.2 Tesla. So it's an FCI that persists to almost 0 magnetic field. So, for now, we can say this rhombohedral graphene Moiré, rhombohedral graphene HBM Moiré system give you FCI in both the weak Moiré potential limit, which that's when you push the electron to be away from Moiré, and when you push the electron to right next to the Moiré, and the electron feels strong Moiré potential. In terms of experimental observation, they are quite different, right? This side has 6 states, persists with 0 megafield, and all of them has positive slopes in Landau fence. While the strong Moiré side all have negative slopes. But at least I feel, if we are still wondering what's going on in the weak Moiré side, maybe we should try to understand what's going on the strong Moiré side first, because there's strong Moiré potential. Okay? And I should note that the 2/3 FCI in that we observed has been confirmed by an independent experiment by Xiaobo Lu's group at Peking University. They use a 6-layer Rhombohedral graphene instead of 5-layer. They observe 2/3 FCI there. So the physics here is repeatable. And in our lab, we keep studying this fractional quantum anomalous Hall effect and FCI using DC transport. Okay? So this is the data I just showed you, and at that time we don't have good filters in our dual fridge. So the electronic temperature now we think is probably like, at that time it was probably like 300 millikelvin. Now we think we can get to something like 40 millikelvin because there's some superconducting state in graphene. The transition happened around 40 millikelvin. And what you can see by comparing the data back then and now is that for these fractions that we have identified previously, the RxX goes deeper. Okay, it's not 0 yet, but as temperature goes down, the dip gets deeper. The smallest residue we have now is like 0.2 h over e squared, about 1 order of magnitude smaller than the value of Rxy. Okay, and because we're at lower temperature, we actually can identify a couple more fractions like 5/11 and 5/9. And we made another sample, which is a tetralayer graphene, and it's a standard Hall bar, and this is probably at the temperature of like 200 or 300 millikelvin. You see the integer quantum anomalous Hall state, and the fractional quantum anomalous state has 3/5 and 2/3. In this case, the 2/3 dip is as small as 0.1 h over e squared. So this FCI physics is repeatable in 4-layer, 5-layer, 6-layer if you combine all the communities effort. Okay. Next, I'm going to show you something that's really unexpected. Again, this is our data, published last year, and this is about 300 millikelvin in electronic temperature. And you can see those fractional states, right? But if you really, cool it down to the lowest temperature that we can access now, you get maps like this. It's the same device, okay? And we don't think there's any degradation because it's encapsulated. What you find is that, okay, you still have dips here that correspond to FCI, fractional feedings. But what really grabbed your attention is that now there are 3 big patches, okay, 1, 2, 3. That shows vanishing RxX and seems to be uniform colored RxY, which was not really there, right? So here you have some anomalous Hall, but it's not uniform. And you don't have this little diamond here at half fading. And this region is, it looks just quite different. Experimentally, we know that now if you do a line cut like this along the dashed line, you find that these 3 regions almost connected into one, that the RxX touches 0. At the same time, Rxy seems to develop a big plateau here at h over e squared, an integer value, even at fractional feeding factor like 3/5 and 2/3, if you cut here. Okay? So something is going on at the low temperature. And in this particular case, if you just look at the map, you actually wonder where's 2/3. Well, 2/3 is not visible anymore. 2/3 is supposed to be somewhere here. But it's completely swamped by this integer quantum anomalous Hall state, this big region. Okay? A little bit more on this, integer, very fragile. You need very low temperature to see it. You actually also need very low current excitation. What I'm showing here is that you can apply a DC current background plus an AC current modulation. And then you can vary the DC current. You keep the AC part very small, and you can vary the DC current from 0 to something like only a couple of nanoamp. That's big enough to cause a qualitative difference. Okay, if you have 0 DC current, you get basically almost the big plateau at h/e² I was trying to show you. But if you ramp up the DC current a little bit, okay, it actually gradually recovers what you see at higher temperature. Okay, simplest explanation is current is heating it up, so it's effectively 300 millikelvin electronic temperature. However, there's some non-monotonic thing going on. As you can see here, from blue, which is the lowest current, to red, which is the highest current. In the middle, there's some like big jumps, okay, in the RxX. So if you park here at the certain filling factor, for example, 0.79, what you find is that at the small DC current, you have RxX almost vanishing, and Rxy is quantized as h/e². This is that fragile integer quantum anomalous Hall state. But when you ramp up the current, you see some behavior that really reminds you of S-wave superconductor if you only look at Rxx. There's a critical current that gives you a pair of peaks in differential resistance. At the same time, the quantization of Rxy will no longer be at the integer value. It recovers what the quantum Hall liquid does. Okay? So that's, I seem to be telling you that at lower temperature, FCI is gone. However, that's not true, okay? So this is a zoom in that region. 2/3 is supposed to be here, and in this particular device, you couldn't tell 2/3. But for 4/7 and 3/5, you actually can see that now the vertical stripe got cut into two parts. The higher displacement field part become the integer, while the lower displacement field part are still there. They are still FCI. So there's clearly competition between this, what we call as extended quantum anomalous Hall state and FCI, and that competition depending on temperature, depending on displacement field, depending on density, and depending on the current. And even at the base temperature with the smallest current that we can use to measure, if you do a line cut like this at 4/7 and 3/5, you still have the majority of the FCI being there. Although the higher displacement field part develop an integer plateau that corresponds to this little triangle here. And for all the fractions below half filling, they are doing perfectly fine. They are still FCI. Okay? So if you remember, we now have like a total of 8 fractions in this pentalayer graphene HBM Moiré system. One of them, 2/3 in this device, seems to be gone. However, 7 out of the 8 are still there. Okay? That's this device. Let me show you another device. It's very similar twist angle. It's actually on the same chip. I call pentalayer device 2. If I just show this big face diagram here, it really mimics what I showed you in device 1. Where they have big patches that has uniform color of Rxy and vanishing Rxx. However, in this device, you can see 2/3 actually has a little residue there. It's not completely gone as in the other device. And you still have the local dip of, at 2/3 in the Rxx channel. And if you really check what is the value of Rxy at this little residue that's still persisting at 2/3, it is still at the fractional value corresponding to fractional filling factor 2/3. Okay? So I'm trying to make a point that in this device, even 2/3 is still there partially, and the Rxy is actually still quantized at a fractional value. Okay? That's device 2. Device 3 is a tetralayer device. Again, if you just look at this base temperature big face diagram, you get the impression, oh, this integer extended quantum anomalous state is taking over everywhere. However, if you look carefully, there's still color that's indicating Rxy more than h/e². Okay, 2/3, 3/5, they are still there. And if you really look at a line cut, you see this 2/3 still touches 1.5, which is 3/2 h/e². And clearly, which state is winning, like FCI is winning or extended quantum anomalous Hall integer is winning, depending on a lot of parameters. And that's one of the big advantages of this 2D system, that you have so many knobs to tune, and you can stabilize different phases in different part of the ND map. Okay? So I think it's fair to say most of the fractions are still doing fine, although this integer extended quantum anomalous Hall state makes the system even more interesting. It's even more rich. Okay? So I took 15 minutes to talk about all this, and you wonder, like, what's the rest of the talk gonna be? Okay, sorry, before moving to that. Okay, so what is this extended quantum anomalous Hall state? Integer value covering a big range of density and the fitting factor. So this really reminds you of the so-called reentrant integer quantum Hall effect in the fractional quantum Hall case, which is saying between fractional fitting factors, your Rxy can go back to the nearest integer value. You can think of that as this, at the integer fitting factor, you get quantum Hall liquid that give you the integer value of Rxy. And whatever the residual charge you have there, no matter if it's electron or hole, form a topologically trivial Wigner crystal. And that doesn't alter the Rxy. Okay? So scenario 1 is maybe what we are getting here as extended quantum anomalous Hall state is an anomalous version of reentrant quantum Hall, because this happens at zero magnitude. Scenario 2 is, maybe this is related to what Ashwin is going to tell you in the next talk, that the electrons spontaneously break translational symmetry and form a crystal that has topology in it, okay? Anomalous Hall crystal. And there are several, relevant authors in the audience that we can discuss later. And in our case, as you can see, the pentalayer, the tetralayer, they have slightly different twist angle. The pentalayer, this integer state, stops at roughly fitting factor 1 and doesn't really go beyond fitting factor 1. While in the tetralayer device, due to the different twist angle, this integer quantum anomalous Hall state actually protrude out. It reaches a fitting factor of something like 1.3. Okay? So if you think of this state as the anomalous Hall crystal, which does not care about what Moiré period is, then this may be compatible with that picture that, it's the absolute charge density that matters instead of filling the Moiré and the Moiré filling factor that matters. Okay? But again, our sample has Moiré in it. We don't really understand what the Moiré does, but you cannot ignore the fact that there is a Moiré. So naturally, as an experimentalist, I want to know if I completely get rid of the Moiré, what's going to happen? Can I still have something like a anomalous Hall crystal at the zero magnitude stabilized by impurity, just like Wigner crystals can be pinged by impurity? And that's the next thing I'm going to show you. Short answer is, so far we haven't found anomalous quantized Hall crystal in the sample without Moiré. But I want to make two notes. Number one, you shouldn't be super disappointed because we haven't searched all the corners. There are things we know we should check, but we haven't. The second thing is, although you don't have anomalous Hall crystal yet, you get some very bizarre superconducting state. That's actually what we'd like to focus on today. And this superconductor looks different from any superconductor that you have seen for the following reasons. Okay, this time, let's focus on tetralayer graphene. We have three devices. Device number one has a WSE2 layer, and it has good contact when the charges are pushed, when the electrons are pushed towards WSE2. So there is strong spin-off coupling. Device two has good contact when the electrons are pushed away from the WSE2. So this may have some weak spin-off coupling, but maybe non-zero. Okay? Device 3 has no TMD. Device 3 is just a bare tetralayer Rhombohedral graphene. And we see superconductivities in all three devices. And guess what? The TC is highest in this one, intermediate in this one, and lowest in this one. Okay? So let me focus on maybe the middle one, okay? Device 2, where there is a WSE2, but the charges in the conduction band are pushed to the layer that's away from the WSE2. By the way, there's no Moiré in all the three devices, okay? This is a big phase diagram taken at the base temperature, roughly 30 to 40 millikelvin. zero magnetic field. And you can actually see that at this region that, if you recall this fractional quantum Ohm's-Hall states, they are residing in a similar range where there's like tilted stripe showing big resistance at low density and something at higher density. If you have Moiré, you'll get integer and fractional quantum Ohm's-Hall somewhere here. Well, in the absence of Moiré, you don't have that, but you do have state that touches zero in the RXX. Okay, there's 4 of them. I call SE1, SE2, SE3, and SE4. Phenomenologically, you probably already noticed that they look very different in the sense that the region of SE3 and SE4 seems to be uniform, while the region of SE1 and SE2 are very fluctuating. Not only SE1 and SE2 are fluctuating, but this big region here next to it is also fluctuating. Okay? And as I said, this region corresponds to when you open up the band gap by using a big displacement field, and you squeeze the bottom of the conduction band to make it really flat, and you put charges in there, and you get these 4 states. Number one thing, the TC of these 4 states are like this, okay? The 2 smooth ones have relatively lower TC, and the 2 jumpy ones, when they are not jumping, you can measure the temperature dependence, and they have relatively higher critical temperature. Yes?
Which temperature is the image shows?
What electronic temperature?
Yeah.
I think it's probably 30 millikelvin. Okay, and now let's look at the S3 and SE4 first. Okay, we apply some outer plane magnetic field, and you can see SE3 and SE4 can be easily killed by a few millitesla or like tens of millitesla. And this is very typical for graphene superconductivity. It's very weak, TC is very low. With the outer plane magnetic field at this level, you can easily kill them. However, this doesn't answer what SE1 and SE2 are, right? It looks jumpy when you do this ND map. You scan the charge density at the fast axis. And it is still fluctuating if you park at a specific combination of the N and D. This is taken inside SE1. You just park there and you watch it as a function of time. You see, most of the time it stays at zero resistance, but from time to time you get a jump, right? A spike or a little plateau before it goes back. It is fluctuating. And there is magnetic hysteresis. If you scan outer plane magnetic field, you get the spikes separating 2 states that both have zero resistance. So this magnetic hysteresis is between a superconducting state and another superconducting state. No other superconductor does this. This is a fluctuating superconductor. And when you apply a 0.1 Tesla outer plane magnetic field, you get phase diagrams like this. Okay, first of all, SC 3 and 4 are gone. Okay, this 100 millitesla is too big for them. However, SC1, SC2, they got stabilized. There's no more fluctuations. Not only in the superconducting region, but in this big region right to the next, there's no more fluctuations. So the system really got stabilized by outer plane magnetic field. And you can, anti-symmetrize the RXY channel to get the Hall signal, okay? As you can see in this bluish region, you have a lot of anomalous Hall resistance. Even to the left of this superconducting state I call SC1, there is a blue stripe that shows anomalous Hall, okay? And that anomalous Hall resistance is real. It's really anomalous Hall because if you do magnetic field sweep, there is hysteresis, both to the left and to the right, okay? So there's value polarization. The 2 values are time reversal pairs of each other. If they're equally populated, anomalous Hall resistance is supposed to be 0. But here, you have anomalous Hall, so value is polarized. At the same time, you can do the quantum oscillation, okay? You apply an outer plane magnetic field, and you count the period of this quantum oscillation to tell how many of the isospin pockets are occupied. You find this region here, which is right to the next of SC1, is a quantum metal. So that tells you this neighboring state is a spin and value polarized quantum metal. It's not inter-value coherent because you broke the value symmetry already. Okay? And there's no obvious quantum oscillations in the SC1 and SC2 region. Right? Here's SC2, here's SC1. There's no quantum oscillation observed. We believe this may be due to the fact that this band is really, really flat. If you do a calculation of the effect mass, probably get something like 2 or 3 times of baryon electron mass. Okay, good. So given that you know the neighboring state to the superconductivity, at least SC1, is a spin and the valley polarized quantum metal, you can ask, can I use that as a probe to tell what's going on inside the superconducting state? The logic is very simple, okay? Spin and valley polarized quantum metal has outer plane orbital magnetization. When you apply an outer plane magnetic field, you can lower the energy of that quantum metal. If the superconductor is not magnetic or not as magnetic as the quantum metal, then the phase boundary between the superconductor and the quantum metal is gonna move towards the superconductor and convert part of it to be quantum metal. However, what you actually found is that this right boundary here remains vertical when you apply magnetic field, outer plane. And the left boundary is even expanding a little bit, okay? That means the superconductor is even expanding to a region that was not superconducting at 0 magnetic field. So instead of magnetic field kills superconductor, for a little range of magnetic field, superconductor actually got stabilized. And we think this tells us that the superconductor itself is an orbital magnet. And that is why it is fluctuating. Because orbital magnet can fluctuate from K value to K prime value, or magnetization pointing upward to downward. And orbital magnetization, orbital magnet can be stabilized by an outer plane magnetic field. Okay, that's why you got hysteresis. So time versus symmetry is broken at the orbital level in the state. And the other thing you can do is, okay, so how about the normal state, okay? If I warm up the temperature to something like 450 millikelvin, it's above the TC, you actually still have anomalous Hall in these superconductor regions. These dashed ovals here outline SC1 and SC2, okay? And if you park inside there SC2, you do hysteresis, you got a loop. You got anomalous Hall resistance, you got the magnetic hysteresis loop in both SC2 region and SC1 region. There's clearly anomalous Hall and hysteresis. So valley and the time symmetry is broken, time versus symmetry are broken at the orbital level before you get into the superconductor. Okay, a little bit more. This is another device. This device has no TMD at all, so don't worry about spin-orbital coupling. Okay, and in general, you got SC1, SC2, SC3, although this device is a little bit limited in the gateable range without leaking. But anyway, you see 3 of them, and this is at 480 millikelvin. You see there is a boundary here in the RXX map, okay? And here I highlight the boundary by this yellow dashed line. At 480 millikelvin, this yellow dashed line intercepts the big SC1 region, and then make you feel like, okay, so part of your SC1 is enclosed in this dashed line boundary, and here's quantum metal, right? Due to quantum oscillation, here's quantum metal. You may get the impression that this little stripe here of SC1 has quantum metal as the parent state. That's true, but that's not complete, because when you cool down the sample even more, this boundary between the quantum metal and this PIP metal state actually will shift to lower charge density. So at 480 millikelvin, it intercepts only this part of the SC1, but when you cool down even more, this boundary shifts to lower density, and the superconducting state emerges to the right of this boundary. And that tells you that the superconducting state really develops within that spin and valley polarized quantum metal. Okay? So this boundary can be seen clearly as a kink in the line cut of RXX. Okay? And if you And you probably notice that this SC1, SC2 persist with very high outer plane magnetic field. Okay, you can estimate the coherence length in that, using that critical magnetic field, and you can compare that to the interparticle distance, which you extract from just the charge density. You find that SC1 is actually pretty close in terms of coherence length and the interparticle distance, and you can put it on this BCS-BEC crossover map that you're close to the crossover, but you're still on the BCS side. Okay, there's some strong coupling, but not very strong. Okay, to summarize, we have 3 observations. We have RXX fluctuation at the zero magnetic field in the superconducting state, and we have magnetic hysteresis. This is absent from all previous superconductors. This tells you it's an orbital magnet. Second, SC1's parent state is within that spin and value porous quantum metal. And this boundary between superconductivity and the quantum metal is not tilted when you apply outer plane magnetic field. Okay? That's consistent with number 1. And number 3 is above TC, you have anomalous Hall, magnetic hysteresis. And this implies that, okay, the superconductor has to be a valley and spin polarized superconductor. Because it's valley polarized, the Cooper pair must have finite momentum, like in FFLO. And it is a chiral superconductor because time versus symmetry is broken. And it's broken at the orbital level. Okay, so it's not like broken by the spin, and the orbital can be a simple P wave, which is not time versus symmetry breaking. This is broken at the orbital level, so it is a chiral superconductor. And of course, you can ask, is this chiral superconductor a chiral topological superconductor? Maybe like PX plus IPY that has Majorana on the edge. We don't know yet. Okay? And then number 2 thing, what is a parent magnetism? I'll leave it open for discussion. And I want to remind you that this is a simple carbon crystal. There's no twist, there's no Moiré, there's no symmetric coupling other than what's already in carbon. Okay? And, we have been talking about rhombohedral graphene a lot. It's a crystalline form of graphene. We have already realized many exciting physics, but to me, there's a whole universe to be explored. And I should note that yesterday, our group and Andrea's group both posted a paper about superconducting ABC trilayer graphene on arXiv. And there are previous effort by other groups on this topic. This is the last slide, okay? It's a very rich system, but experimentally it has been very challenging to fabricate the device because rhombohedral is not the most stable form. So I am showing you what we are doing now to help fabrication of such devices. So all the experimentalists in the audience and the people watching this online can have a slightly easier life, okay? So this is the version back in 2010 when Tony Hines' group used Raman spectroscopy and mapping point by point to reveal the stacking order. And later we figured out you can use an infrared nanoscopy to map it out, which shortens from hours of time to minutes of time. But I was asking myself, wouldn't it be nice if I can just see the stacking order? And by seeing the stacking order, I don't mean by scanning anything. I just want to see it. And indeed, you can do that, okay? All the secret is that you use an infrared camera that's made out of ink gas. And you can look at this flake here and see all this internal structure that you cannot see from a visible light. So less than a second, you know where's rhombohedral. And you can do this through the whole process that will boost your yield. Okay? This is all my secret. I'll stop here.
Do you know what's the origin of the switching noise and the time scale of the noise?
In that particular plot, it looks like it's like minutes, 10 minutes scale.
So what sets that time scale?
I do not know. For the 3 samples, they have different time scales. But the fluctuation in the superconducting region is always correlated with the rate of fluctuation in the quantum metal. And that's all what I know. at this moment. Yeah.
How does the critical current of the quarter matter superconductor change with magnetic field?
Yeah, I think we have a plot like that. At the zero magnetic field, I think it's probably 20 nanoamp critical current, and when you apply magnetic field, of course, it goes to be smaller. But I don't know exactly what you want, but I can show you later.
Okay. Yeah. Because I was thinking you apply out of plane field and superconductor doesn't get suppressed, so. No,
it does. I mean, it's just it takes about 1 Tesla to completely kill.
Okay. So up to 1 Tesla, critical current doesn't move, basically.
No, critical current shrinks as you apply magnetic field.
Okay.
But if you're staying close enough to zero current, it's still superconducting.
Okay, thank you.
Do you have any signatures of? That's me. Okay, yeah. Do you have any signatures of phase coherence near boundaries of the superconductor? Any like Fraunhofer type wiggles?
I don't think we have time. We haven't got time to do that yet.
So you had 3 samples
yes.
with different, strength of spin-orbit coupling, right?
Yes.
So how does superconductor strength depend on the spin-orbit coupling? So
the sample without TMD at all has the highest TC of BKT of 300 millikelvin.
Okay.
And the one that has some weak spin-orbit coupling is about 210, and the other one has strong spin-orbit coupling is like 160 millikelvin.
I see. Uh-huh.
In all of those 3 samples, you don't see any integer churn insulator, right? In all the unaligned
not
samples.
Yet. Not yet.
Well, what's the region of parameters that you've tested compared to the aligned samples?
I think we probably covered.
What do you mean by not yet?
A big enough ND map. But we have other samples like 5 layers, 6 layers that we're still testing now. Yes.
Okay. And about the aligned samples, am I correct to assume from your data that at nu equals 1, increasing the D field, the displacement field, you get metal, churn 0, churn 1, and then metal, and the churn 0 state also increases in D region upon cooling down. Is that
okay? So, I'm sorry, it's a bit too much. for
nu equals 1. I'm just asking the sequence.
Nu equals 1.
Nu equals 1 as a function of D. Is it metal, churn equals 0? I see a highly resistive state there. Churn equals 0, churn equals 1, metal.
That's right.
And the churn equals 0 region increases upon cooling down also.
Oh, I didn't pay attention to that, but yeah, so I don't know, but we can take a look later.
Have you applied in plane field to check these Pauli violations?
Short answer is we don't have a vector magnet.
So it hasn't been checked yet.
So we haven't checked it.
Yeah.
But maybe it's not terribly difficult to do because outer plane critical field is already 1 Tesla. If you have a small misalignment, maybe fine.
Yeah, and also kind of how that in-plane magnetic field will just change the phase boundaries around. I think that's also kind of very interesting information.
I agree.
Right?
I agree, yes.
In your phase diagram, I think, for the tetralayer superconductivity, I noticed another region with a small resistance, but you didn't.
Where?
The initial one. Yeah, like below the...
Oh, you mean here?
Yeah.
No, that's not 0. I mean, black here, I believe, means very big and fluctuating.
Okay.
I have a question really quick. Can you go back to the time-dependent resistance? One slide, or forward. How do you know it's a property of equilibrium? I mean, how do you know it's not out of non-equilibrium property of the superconductor? You're driving it with current, right? You're heating it.
Yeah.
How do you know this is an equilibrium
as small as
property?
I can measure.
Okay. It looks like a non-equilibrium
I think we're using the smallest current that's above noise level to measure.
I see.
Yeah.
Thank you.
So you mentioned that one of the superconductivity you have is possibly FFLO state. Have you tried to look into if there's a translation symmetry breaking out of it?
How do I measure that?
Freedom STM.
I wish Ali can figure out how to do STM on this, but as you can imagine, it's still gated, so it's not easy.
So it's not easy. I see.
Yeah.
Thanks.
We have time for a couple more questions.
Thank you for the very interesting talk. Do the other superconducting domes show a similar magnetic hysteresis? You had like 4 of them, 2 of which kind of had this unconventional character, 2 didn't. Is this magnetic hysteresis similar for all of them or not?
It's probably similar for SC1 and SC2, but not 3 and 4.
Sorry, which were those 2? Which was 1 and 2?
1 and 2 are the jumpy ones.
But 3 and 4 did not have it.
No, 3 and 4 just look like, especially 4, you see it's at some phase boundary, and that's probably similar to seeing bilayer and trilayers where maybe isospin fluctuation is mediating superconductivity.
Gotcha. Thank you.
So in the previous slide, when you switch the magnetic field, so you have the different peak in, this figure. So is there any difference in these 2 time reversal opposite superconducting states?
Well, they're both superconducting, so I couldn't tell. I mean, they're both 0 resistance. So one is polarizing K value, the other is polarizing K prime value. That's what I think is going on. But experimentally, they're just 0 resistance.
Mm.
Yeah. So is the right picture to understand this is that you are in a quarter metal, it's fully valley polarized. The reason normally you wouldn't expect to get a superconductor is that you don't have inversion symmetry. But here you have such a large effective mass that the kinetic energy doesn't actually matter that much, and you're just pairing in a flat band where K is not even a good quantum number. That's kind of what you're thinking.
Yes.
Okay.
Yes.
Sorry, one last question for me. So in the FCI, the 2/3 disappears, but let's concentrate on 3/5.
Okay.
If I now plot, you said that it's still there in a region of smaller d.
Yes.
But I want to plot that region as a function of temperature and see how it goes to t equals 0, right? So do you have that plot?
No, we do not have it yet, but clearly that's something we should check.
Right. So we cannot claim yet that it survives or not survives at 0 temperature, right?
Oh yeah. So as I told you, I think the electronic temperature is probably like 30 millikelvin now. At this temperature, you have the majority of the 3/5 still there.
Maybe one last question. Oh, thank you. I see you over there.
You talked about this PIP and the quarter metal, the phase boundary being one of the boundaries of SC1, I think.
Mm-hmm.
So does it mean this SC2 is in the PIP
So
region?
as you can see, this is probably the quarter metal region, and somehow SC2 is an outlier, although it's neighbored by it. But above SC2, it's not quarter metal.
Mm-hmm.
I mean, this pattern is too complicated to be a quarter metal.
Mm-hmm.
So I don't know why. It feels like if you just look at the superconductivity, there should be a big oval that's superconducting, and then it's cut through by the phase boundary between quarter metal and PIP.
Mm-hmm.
So I'm less confident about what SC2 is, although I think it's still valley polarized and it has to be FFLO, because even if it's one big K pocket and slightly smaller K prime pocket, you do have finite momentum for the Cooper pairs. But SC1 is more like clear in that sense.
Really quick.
In the quarter metal region, you have a shift along some boundary in the quantum oscillations.
You mean somewhere here?
They're not perfectly vertical, right? There's some boundary at which they shift. Do you understand what that is?
I think that, probably Ali can answer this question, because remember he was telling me that they understand now why sometimes there's a shift of this quantum oscillation features. Yeah, maybe we can talk about that later.
Okay, let's thank Feng Ju again.
Yeah.